In this video, we're going to look at the at limits that do not exist. And so in here, we have this way to shorten it up, and we would say that the limit as x approaches some finite value of f of x does not exist if f of x does not approach the same value from both sides. Now, same single value. And again, if we're talking about approaching a finite, x approaching a finite value, not going towards an infinity or negative infinity, which we'll talk about in a different video, that can usually happen in one of three ways. The first example we have, I tossed in this function. So before we evaluate this, let's see what this is. This here is what's called either the floor function, so this is the floor, or the greatest integer function. And it's the greatest integer that's less than or equal to x. So greatest integer less than or equal to x. So the floor of 2.3 is equal to 2. The floor of 5.9, it's not rounding, it's bringing it down, is 5. The floor of 6, well, the greatest integer less than or equal to 6 is 6. And the floor of something like negative 1.3 is actually negative 2. That's the largest integer that's less than or equal to negative 1.3. So it doesn't just drop the decimal. It's sort of the round down function. And in order to evaluate this limit, let's consider its graph. So I'll do a quick sketch here. We can graph this in the calculator. I'll show that next. I'll start at 0. So the floor of 0 is 0. And let me put in a scale going here. Alright. So I can make this a little bit neater for us. If I put in something like 0.5, the floor of 0.5 is still 0. Floor of 0.9 is still 0. So everywhere from 0 until I get to 1, the floor of that value is 0. Then when I get to 1, the floor of 1 is 1, so it jumps up. And for every x between 1 and 2, including 1 but not including 2, the floor of that is 1. So take, for instance, the floor of 1.3. Floor of 1.3 rounds down to 1. When I get up to 2, it jumps up to 2, and everything from 2 to 3 has a value of 2, and then it jumps up to 3 and keeps going this way. On the left side, it is included. On the right side, it's not, and I'll fill in the other side, same reason. Alright, looking at this specific example, I want to approach 2. But we see as I approach 2 from the left side, my value is here at negative 1. When I approach 2 from the right side, sorry, not negative 1, I don't know what I'm thinking, my value is approaching 1. When I approach x from the right side, my value approaches 2. It doesn't actually matter that f of 2 is 2. I don't care what happens at 2. I never care what happens at the target value. I'm approaching two different values, so the limit as x approaches 2 of the floor of x does not exist. Now, before I go on to the next example, I do want to stress we see all of these jumps, and this is caused by the jump. That doesn't mean that none of the limits exist. So, for example, if I wanted to find the limit as x approaches negative 0.5 of the floor of x, I want to approach negative 0.5, which is right here, and I only really care what's happening close. So it doesn't matter if I'm very far left, that'll be down here. As I get close to negative 0.5, I'm approaching the y value of negative 1 from the left and from the right. So this does in fact have a limit. So the function is not the case where it doesn't have a limit everywhere, at least this one. There can be some really wacky functions that do, but everywhere we have this jump, we will not have a limit. So that's one example. Oh, and I guess I said I'd show the calculator. So how I can put this in here, and it's the same thing that I would do for programming, is the int. I'm sort of casting it as an integer. So if I go to math, over to num, int is the fifth thing, and this is the floor function. It looks like steps, so we see, and it's also called the step function, there should be jumps here, but it's connecting it up. So I can fix that, I believe, by going to mode, and instead of having connected, I will go to dot, and that will get rid of those, where it's only plotting the points that it actually has. That can cause some problems. I'll show you how to fix those in the next example, I believe. But there we have it. Notice the calculator doesn't tell us what's included, what's not, but it gives us the right idea. All right. What about this one? Well, from earlier courses, we should know that the graph for tangent looks like this. We start negative, we come through with a slope of about 1 there. We'll talk about why that is later on. Not in this video, but in a later video, when we start talking about the derivatives of trigonometric functions. And it continues this way, with these asymptotes at negative pi over 2, pi over 2, 3 pi over 2, negative 3 pi over 2, and asymptotes at pi over 2 plus k pi for all integers k. So, repeating here, I'm considering the limit as x equals pi over 2, or as x approaches pi over 2, and so what I do is from the left, if I try to approach pi over 2, which is right here, from the left, I'm pointing upwards towards negative, or towards positive infinity. But from the right, as I approach pi over 2, I'm pointing downwards towards negative infinity. The fact that I'm not even pointing towards the same infinity means that the limit as x approaches pi over 2 of the tangent of x does not exist. But as with the previous problem, there are many points in here where it does exist. Most of the points, this limit does exist. So if I instead considered the limit as x approaches pi over 6 of the tangent of x, well, I know that pi over 6 is going to be somewhere about here, where the sine of pi over 6 is equal to 1/2. The cosine of pi over 6 is equal to root 3 over 2, which means that the tangent of pi over 6 is 1/2 divided by root 3 over 2, which is equal to 1 over root 3, because I can multiply the numerator and denominator by 2 and cancel out the fractions. And I can even rationalize the denominator and get root 3 over 3. Now, I can do this here because it's continuous, where x equals pi over 6. If we didn't know that, we can see that, okay, it is approaching that value here. And that's eventually going to be how we know if it's continuous or not. So again, just because the tangent function has a bunch of these infinite jumps doesn't mean that it is that it has limits nowhere. Most of the places we're good. And then one more. This one's a little bit strange. So we have 1 over x here, and we know that that's going to go very badly near 0 because this will be undefined. But what actually happens in this case is this. So I'm just doing a quick sketch. We'll look at the calculator in a little bit. Sine oscillates between -1 and 1, and what's going to happen is it's going to start oscillating faster and faster and faster. It's not defined at x equals 0, and afterwards oscillate, and then ease back out. It's actually an even function, which is kind of fun. So this is sine of 1 over x. And here's the problem. As we are approaching 0, I keep on going between -1 and 1. And regardless of how tightly I bound this, tightly I squeeze x, you know, we talked about some delta epsilon stuff, no matter how small I make this delta, I'm still going to have some points where it's going between -1 and 1 because 1 over x actually sort of explodes out to positive and negative infinity. It goes out very far, so it gets all these oscillations in. So, because I don't actually have it approaching a single value, I will know that the limit as x approaches 0 of sine of 1 over x does not exist. I'll look at the calculator so you can see what this looks like here. So, in this one, I'll do sine of 1 over x. There's going to be a problem with this. I'll show you that shortly. So I graph it. It's not very interesting right here. Okay. Oh, I think I might have lied to you. This one's actually an odd function. But when I zoom in, it's not going to show me what I want to show, and I'll fix that shortly. Oh, zoom in some more. And it's not giving me very many points. The reason is the calculator is not smart. It doesn't know what it's doing. It just tries to plot a few points and it's connecting them up. So if you had a sort of better graphing utility, maybe a TIN spire, or if you use GeoGebra, you'll see this oscillation going much better. There is something that is worth noting though. So the reason that this messed up wasn't just based on the 1 over x. So this is the answer to this problem. And yeah, the 1 over x caused the problems, but just having this in here doesn't ensure that I have a DNE. For instance, if I wanted the limit as x approaches 0 of x times the sine of 1 over x, then this actually has a limit. And we'll see why a little bit later. It's called the Sandwich theorem. But let me put that in. So x sine 1 over x, and what happens, let me put times there just to make sure it does it correctly, is it still oscillates a bunch, but you can see through the oscillations, it's actually approaching 0, regardless of the sort of shakiness of this. So even though it has all these oscillations, it's still going towards 0. Alright, if you have any questions, feel free to comment below, and I hope this helped you out.